Thank you, Mr. Chairman. It was indeed a pleasure to be asked to come here to give my reflections and recollections of what clearly is regarded as a key segment in computer history. And I was present at close to the beginning of this remarkable saga, and in a strange way, which I'll explain at the end of this talk, I was there at the end also. It was in late 1943 that I, as a young naval officer at Naval Research Lab in Washington, met Howard Aiken, who induced my commanding officer to have me come back to Harvard, which I had only left a year or so earlier, to work on a new calculator which was about to be delivered to Harvard. It sounded intriguing to me. It frankly sounded much more intriguing than the activity I was involved in, and I was delighted to come back to Cambridge, which I did in March of 1944. At that point, there were three members of the scientific staff. There was Commander Aiken, a gentleman by the name of Robert Campbell, a young graduate student at Harvard, who, by the way, is still active in the application area of this field at MITRE Corporation. And then there was myself, and the machine actually arrived just shortly before my arrival, and I will get to impressions that I had in a moment on that. What was the genesis of this machine? It's been well documented that Howard Aiken had written a paper which has been preserved in 1937 entitled Proposed Automatic Calculating Machine. And as he put it, this emanated out of a stress which he felt in running rotary calculating equipment in the attempt to solve some nonlinear, attempt a numerical solution of some nonlinear equations that he was working with while obtaining his doctorate at Harvard. And he became exceedingly frustrated and thought that there must be some way in which this calculating system, which he had to deal with, could be improved. I would suggest that if the paper is available and can be made available to anyone like it, that it is a document which bears reading. There's much between the lines as well as on the page, and it I think makes clear much of what happened later. And I mean probably for much of the total Harvard period. I think it explains the man and his motivations and his thoughts quite well. His ideas were essentially that of combining a number of machines in some form of a switchboard control array, so that there could be a sequence of or path from the conclusion of one calculation to the input of the next. And he described in the paper the way he thought something like this might be done. But it wasn't until he had taken his ideas to IBM in 1939 that he had the opportunity in collaboration with some key engineers at IBM to formulate what became the design eventually of the Mark I. I might add that Mr. Watson was personally involved in the decision to assist in the design and to build it and to fund it. Without which one can conjecture whether the machine would have ever been built. So in 1939, design and construction began at Endicott. People have asked me, since I have known Howard Aiken very well, both in a personal sense and in a professional sense, and we were able to talk with each other quite freely as to questions concerning his role in this design. And apparently the basics of what we would call the logical design really were his: the configuration, the organization, the total concept, and many of the special features which I will go into later, including special functions internal to the machine, interpolation, and so on. But the interesting thing was that this had to be built out of essentially available components, and the components which were available were tab components, in some cases modified, in other cases really not. As a result, this machine, when it was constructed, had thousands of relays which were essentially identical to relays that were being used in the tab machine line, counter wheels, which were also taken directly from this line. And of course, it also utilized card feeding and card punching equipment, which were taken directly. And it utilized a series of typewriters, as a matter of fact, two, which were fitted out with solenoids to enable printing to take place directly from the machine's control. Well, to move back to early '44, the machine was impressive, if not awe-inspiring. It was over 50 feet long and about 8 feet high. It had another unique aspect. You'll never see this again. Although I'm told that we're going full circle, so we may get a rebirth here too, but I doubt it. The machine was driven by a shaft. A huge shaft, the length of the machine, for all 50 feet of it, which drove through gearing vertical shafts at intervals of approximately 8 or 10 feet, which in turn drove horizontal shafts. And now we're getting close to what the purpose of this was. Those horizontal shafts were driving the internal mating wheels of the electronic, pardon the word, of the tab counter wheel. And so that the interesting thing here was that when power was applied to the machine, that is to a relay bank, and eventually power applied to the armatures here, this was really a type of elementary servo system, because what it simply did was to pick up the armature and then let the power of the shaft system move the counter wheels, which would move a number of positions depending upon cam timing. And I purposely don't want to go into details on this, and you'll also note that I have no slides, and the reasons for both are that unlike the situation, unfortunately, with several of my colleagues here, this era, largely due to Howard Aiken's insistence, is superbly documented. And you will be able to read and, I think, understand very easily the entire principle of the machine by simply obtaining volume 1 of the Annals of the Computation Laboratory, Harvard University, published by the Harvard University Press, I believe 1946, in which this machine is not only described in detail and given as a manual of operation, but has the following as well: detailed programming and programming guides with multiple examples of how to program the machine, taken from real life, taken from actual programs that were used, together with a complete series of wiring charts, relay charts, and everything else. It is really something which I well remembered as I went on to industry after that, because I'm afraid the people that I was associated with, and they were some quite reputable operations, hardly ever did a job approximating this type of documentation. Just a few details, though, so as to position this machine. It was decimal, and Howard Aiken preferred decimal to binary forever after. Of course, this was decimal in a quaint way. This was not binary coded decimal, you understand. This was true decimal. You might say the mechanical equivalent of a ring, an electronic ring. And the speed was, by present-day standards, a little on the slow side. We had the following: an addition or a subtraction, 300 milliseconds. Multiplication, about 5 or 6 seconds. Division, about 11 to 15 seconds, and these were variable speeds depending upon such matters as the number of significant non-zero digits in the multiplier and the number of comparisons that were plugged for a division and so on. But that was rather speedy compared with a very ingenious construction for some transcendental functions inside this monster, which showed the following. Log x, base 10, was computed to about 22 or 23 decimal places, but it took 72 seconds. And the machine also had the functions 10 to the x, and it had the function sine x, both of the order of a minute. But the interesting aspect of this was that if you study the principle that was used, you cannot help, and I do to this day, admire the design of this functional area, because if you think about it a minute and realize that this machine operated from 10 to the 23rd to to 10 to the minus 23rd, depending upon where you were placing this decimal point, and that these transcendental functions computed to any argument in this range, automatically, it was quite an accomplishment in logic for that day, and maybe for any day, in a sense. This was all done, of course, by relay, and which were, by the way, powered by a motor generator set operating when in its best condition at 50 volts DC. And when I later explain the amount of work that came forth from this machine, again, I think you cannot help but admire the design foresight for that day. In many later machines, the quantity of work may not have exceeded what the Mark I put out, despite the speeds that I mentioned. I might add that when Howard Aiken was very proud of this machine, and one of the first things he did was to take a group of graduate students at Harvard, both Radcliffe and Harvard, through the basement of Cruft Laboratory, where this was located, and I thought you might like to hear a few choice tales that at least I was privy to. When he took this group through, one young lady who was wide-eyed said something to the effect, look, this is typing all by itself. And Aiken said in his smoothest way, and he could be extremely smooth, yes, this machine can do anything a human can do, but it does it a lot faster, with one exception, and that is to reproduce itself. And then he smiled. He said, "But we're working on that modification right now." And this young lady nearly fainted on the spot. He did have a sense of humor, although those that confronted him and did not produce the way he thought they should will never attest to that. We also had what I like to call an first audio-visual error detection system, and that is this machine, because of the counter wheel design and the fact that when it was quiescent, you would simply hear the wheels turning relatively quietly throughout the machine, but when the relays were on the counters were pulled, you got this noise which is almost indescribable of the whirring counter wheels sounding like about 200 people cracking their knuckles. And Aiken was on the other side of his office was on the other side of this machine, and I can tell you that when that clicking sound stopped, that was the audio part of it, all you could see was Aiken flying out from his office, wondering what was going on, and that was the visual. And then there was some more audio, but I won't go into that. The machine was run literally 24 hours a day, to which I can attest, since there were several days when I never saw a bed, and I can attest to his generosity here, because after one instance of 2 or 3 days, he let me retire. And I can also say this, though, that I would have wished to have seen this man in a different environment somehow, namely the true industrial environment in the height of his career, because the one thing that he had above all others that certainly I have ever seen was the ability to get work done and an inexhaustible energy. It was my duty. I was not only chief programmer, I was also chief designer of the modifications for the machine, and I was also chief maintenance man. We were still in Navy uniform, and he pointed out that the armed forces weren't stopping, and by God, we weren't going to stop, and we didn't. And I would come in on call at any time at night if the machine stopped and they couldn't get it started due to any sorts of trouble. And I can tell you that on almost every occasion when I did come in, and this would be 2 or 2:30 in the morning, Howard Aiken would be there within a half hour, and he thought nothing. And his regular time of arrival was something like 5 or 5:30 in the morning at all times, so that you can imagine what happened in one instance when he arrived. I wasn't called. The reason I wasn't called, the machine was not down, but one of the operators was, and was dozing away, and we weren't sure whether there was going to be a court-martial immediately or just what. It was touch and go for a period there. I'll say more about him later, but I did want to try to give you the color of the day. Some of the applications early applications that were programmed on the machine, for the sake of the record, were some antenna field calculations. That was, I think, the first. Optical ray tracing came right after that. Then a multiple correlation dealing with impurities in steel. And then we got into this was one of the more difficult problems, a nonlinear second-order differential equation, which John von Neumann brought to us in mid 44, and I had the privilege of working with him at that time in putting this equation on the machine. I might add that it was a very, very difficult problem to one of the classic problems in differential equation theory, and he was very patient with this machine. When you realize that due to boundary conditions and discontinuities and so on, we had to pull down to a mesh for differencing, which was extremely fine, and let alone the speed of this machine in one dimension, you can imagine what it was in two. And it was really three. And nevertheless, that problem was solved numerically. I found, to my chagrin, in checking with Harvard at Gordon McKay, that they had no record not only of that, at least they did not have it in the library, nor did they have any of the other early programs. And it happens that I have some of these, and if by the way, in particular, if anyone is interested, I brought with me actually that particular solution, which was in true Aiken style, very well documented. John von Neumann, in his usual graciousness, allowed me to sign above his name, which in no sense reflects who did the work. Then we went into what many of you have probably at least heard of, and that is tables of functions. And this was a favorite of Aiken's. It wasn't necessarily a favorite of mine. I had to program it, and we calculated to give the following small tidbits: the Bessel functions of the zeroth order. Let's see. Rather, of the first kind, from order 0 through 135. And as I recall, the interval in some instances was of the argument was 1,000th, 10 to the minus 3, and in other instances 10 to the minus 2. But this was done, if you would believe, I was forced to do this to 46 places of decimals, which the machine could manage through a ganging operation. And in order, of course, to stay away from errors, both due to recursion and inherent, as well as round-off errors and so on. I can say this: I don't know whether any errors have been found in the Harvard tables, but I at the time compared with tables, as I recall, of Hayashi for one, which was calculated out to a number of decimal places. We did find some errors in others. We rechecked, and it appeared as though this was a perfect run. Someday I'd like to find out if that is true, but I don't know who's going to make the comparison. The machine. The machine was also used for sine, cosine, and exponential integral functions. And one of the interesting aspects here, I appreciated because we had problems later with printing way past this era. And the problem was not so much design as it was caliber of print. As some of you may know, that's in the business world a rather important demand. And I've never seen any better caliber of print to this day, than came forth out of the Mark I. And of course, the reason was that this was done. Aiken insisted that these were not to be recast, and so direct photo offset process was used off the output of these machines, but in order that it be done properly, we used a special carbon ribbon. And to give you some idea of the trials and tribulations, remember that this was directly connected. And remember that errors, that is machine errors, were known in this day too. And that one digit wrong or one smudge or anything of this sort on that sheet, and we would start over again. For example, in these Bessel functions, so that we really had to be extremely careful. But again, I think you would be amazed if you would obtain or just glance at one of these volumes to see the caliber of print that came forth and realize that that was a direct output of this machine. I'm purposefully, of course, taking this time with regard to the Mark I because this was clearly Aiken's dearest accomplishment. Much went on after that. The Mark II came in November, was proposed to the Navy in November of '44. It was an all-relay design. Relays were used for storage as well as control. And then design started in '45 and was delivered to Dahlgren in '48. I won't go into any further detail on that, but once again, this is completely documented in another one of the annals. The Mark III came, which was the first electronic machine out of Harvard, and I knew what Howard Aiken's reaction was there, and he really was not happy for some time about electronics, and I might say some of us that went on after that weren't happy for a while either, but he did proceed with this magnetic drum machine, and I'm not going to contemplate how it stacked chronologically, but it certainly was one of the earliest magnetic drum machines to my knowledge. That was started in 1948, completed in 50. The drums were 6,900 RPM affairs. This machine also, by the way, used magnetic tape. It was one of the earliest machines to use magnetic tape, albeit, as I recall, that tape was paper tape with an oxide coating. Finally, I do want to say that the Mark IV, which followed on Air Force funds, was completed in 1952, and this machine was one of the first machines to use magnetic cores, albeit not in the 2- and 3-dimensional configurations that we're accustomed to for core memory. This was known in its day as the static magnetic delay line, and emanated from work which went on, original work at the Harvard Laboratory. I don't know whether you people are aware that although the concept of bicoordinate selection and superimposed current selection of cores appeared to emanate from MIT, the concept, as best I can determine, of a static magnetic storage did come from Harvard in the person especially of Dr. Wang, presently president of Wang Laboratories, and also with some assistance from Dr. Wu, president of another company. So much for this. After the Mark IV, and may I just have a minute to, after the Mark IV, Howard Aiken moved the laboratory over to applications attacks, and once again, there are some 50 journals, huge volumes, embodying the investigations and the analytical work, both in computer design and applications to many disciplines of the computer sciences. I would like to say that in discussing what came out of Harvard, I think a great deal, but not necessarily was it by any means all hardware. As a matter of fact, in view of the fact that hundreds of people that have moved into the computer industry from levels of presidents of companies to professorships elsewhere, and I'm not going to list but 0 of them because it would be doing an injustice to others, but they were trained at Harvard. Aiken held symposia at Harvard. These are also documented. I participated in these early symposia, and many of the famed pioneers did, and make some very interesting base reading for anyone interested in the history of this field. Aiken was a tremendous leader, a great inspiration, tough taskmaster. I want to simply say that, which is a curious turn, that I knew Howard right to his death, and that I would like to tell you that at that time he was working on the following, which I can attest to, since I was involved. He had in mind developing a miniaturized computer using where the miniaturization was not only in the circuitry but in the input and output devices. He was working on whether it be a business or a home or a portable computer that would have a small cassette and so on. I won't go into further detail, but that and second, would you believe, a non-impact printer, which he was a co-developer on, and which is being worked on even now, using the micro techniques of today, and then some. And then finally was involved, as some of you may know, in some data security and encrypting applications involving pseudo-random number sequences, and in fact had a patent issued on that. And the reason I mention all of this is that some people have said to me, well, in his day, yes, but eventually, of course, things got away from him. When you realize this man was 73 years old at this time, it didn't look to me as if things had gotten away from him very far. It looked as though he had come back to the world, and I wonder what would have happened had he lived another 10 years. In finality, let me say it remains for the future to put this man in proper perspective, and I hope I've helped give you some insight into this era. Thank you.
Thank you very much, Richard. Corbateau, you have the microphone.
Corbateau, MIT. In a large fraction of the problems of mathematical physics, you need the Bessel functions of both the first and the second kind. Can you shed any light on why he chose to only work on Bessel functions of the first kind?
I don't. I recall that this was brought up, and as a matter of fact, I had offered to proceed on that, and my recollection is that he was. He said we will at some later time, but I certainly left the laboratory soon after I had coded this function. By the way, the programming would have allowed, of course, the further expansion of that, and that's all I can say on that.
Rochester.
Rochester, IBM. There were two of the great pioneers of our field connected with the Mark I. The other was Frank Hamilton of IBM. I would say in modern terminology, Aiken was the architect and Hamilton was the engineer.
Yes.
And now let me just finish it up. Let me relate this to other things that you've heard about, other important things. Frank Hamilton was the engineer in charge of the SSEC. The architect was Rex Sieber, who came from Harvard. And then Hamilton supplied the drums of the 700 series, and after that he started the 650 project, which was completed under his direction with Ernie Hughes being the engineer and Elmer Kuby the architect. And so this man, Hamilton, is really one of the very great people. He wasn't known much out of IBM, but he did a great deal.
Yes, and his name is mentioned in the literature, and I believe, as a matter of fact, that he designed the multiply-divide unit, if I'm not mistaken, of that Mark I also.
Randall.
Aiken's 1937 paper is very noteworthy for the careful summary it gives of prior historical work on calculating, up to and including Babbage. It was preceded a year earlier by a paper by Vannevar Bush, which similarly suggests the work of Babbage and the idea that connecting together a set of punched card equipment, standard punched card equipment under a central control, would be a modern equivalent of Babbage's original conception. Mm-hmm. Do you know of any links between these two men and these two ideas?
No, I don't, but I'm increasingly of the opinion that we ought to really do it doesn't answer your question, but that we ought to do measuring a little more by accomplishment than by time, and I now that the subject is brought up, I simply would like to say that I think this man is an example of something that has been alluded to earlier, and that is whatever you want to say about concept and where it came from and so on, This man was a doer, and whatever he set out to do, he completed and did it in a fabulously short period of time. And one's got to give a great deal of credit to that. I have no answer for your question.
Nelson, you may not have known it, but that problem, the partial differential equation that you solved in 44, was a problem we did here at Los Alamos. And we at that time had a punch card center, and von Neumann had the idea that he would give you a test by giving you one of our problems, and then we'd conduct a race to see who would get through first.
Who got through first?
Well, it took us about 2 weeks to compute it out here, and about 2 weeks later, von Neumann came back and said, "You'd be interested to know they're about halfway through." At first, we were quite exultant and that we had won the race, but then we thought it wasn't maybe a fair one for several purposes. One, we were set up as a production computation center running 24 hours a day and quite used to turning out problems. And this was one of your first ones where you're getting used to the machine. Second, we did it to 6 digits, and you were doing it to 23. And the nature of the differential equation is if you were going to take advantage of the 23 digits in the differences, you would have to use a very fine interval, and that forced you in the other dimension to have a correspondingly fine interval, so you had to go through many, many times the computational steps.
Yeah, there's one other possibility, and that is since I had programmed it, that might have been another reason.
Lubert, Dartmouth, you've been alluding to the documentation. There's another source of documentation that might interest you, which you may not be aware of. Beth Stoll, who wrote the article on the Mark I in the encyclopedia, and who worked for Henry Tropp on the Smithsonian project a couple of summers, was a graduate student in the history of science for I.B. Cohen there, and did a fairly lengthy paper on it, on the history of the machine from the viewpoint of the historian.
Right. I haven't seen the paper. I'm aware of the work. I've been made aware of that.
I can give you a copy. She's my daughter.
Van Wijngaarden, Amsterdam. I think you said that you were not aware whether there were any errors in the Bessel function tables. Now, the Bessel function tables contain at least one error, which was spotted by J.C.P. Miller, which could, however, have been spotted by anyone who took the care to look at the page, because one of the entries is 1 digit short. The worst is, however, it's not the last digit which is missing, but some of the digits in the middle.
It's very interesting, and it's very interesting. I'm glad, and
I know that it troubled Aiken no end.
I can imagine. As a matter of fact, it probably did shorten his life.
I want to thank you very much.
Thank you.